and welcome back. And today I'm going to do practice problems from the end of chapter 10, the interactions and potential energy. And to do that, I'm going to restart with just a quick review for the work energy theorem and then the conservation of energy and how it came up. So I think it's worth, I think we did it like 2-3 times. It's worth coming back to it, and I'll just do it in the case of one dimension only. So remember, in one dimension, we mentioned that the force, the work done, will equal to, if the force is variable, will be the integral of the force dx. And the force is understood to be, this is the parallel part between the force and x, between points A and B. So let's say you have an object, it's at point A, and then you take it to point B. You take it to point B, and you apply a force to it, maybe this way, or maybe this way. This is just the net force. And you go from here to here, how much work have you done? This is it. That's by definition. The second definition is that the kinetic energy is defined to be 1/2 mv squared. 1/2 mv squared. So we looked at the work energy theorem. So let me do it again. Let's take the derivative of, this is definition, so it's always correct. It's a definition. It's neither right or wrong, it's just a definition, I should say. And this is the definition of work, all right? So let's take the derivative of the kinetic energy with respect to time. Now the velocity, because you have a force, it may or may not be changing, so we have to take the derivative here with respect to time. So when you take the derivative, the mass is constant, so the derivative of v squared is 2v, so it cancels the 1/2, so you get mv. But then you have the chain rule, you have to take the derivative of v with respect to time, so you get dv dt, which is equal to the acceleration. So I'll put the acceleration in front of the mass, so I'll just have the mass times the acceleration, and then the velocity. And the mass times acceleration is the net force on the object, so it's the force on the object times the velocity. And I would like to know what dk is. So remember, dk, the differential dk or dy, will be dk dx, dk dt, dt. Okay. So let's see what we get. dk dt is the force times velocity. It's F times v and then dt. But v is dx dt. So let me go here again. So I have F and then dx dt dt. dx dt is the differential dx. So dk will be F dx. And now let's integrate this from the initial position to the final position. So when you integrate that, the integral of dk is k evaluated at points A and then at B, so it will be the kinetic energy at point B minus the kinetic energy at point A. So you will get, let's write the integral signs from point A to point B, from point A to point B, and the integral of dk is k, and then you evaluate it between the limits. So I have k evaluated between A and B, and this one will be, I will keep it as an integral a b f dx, and that's the total work done between points A and B. And so this is just the kinetic energy at point B minus the kinetic energy at point A, which we call the change in kinetic energy, and that is equal to the work done. This is the work energy theorem. It says the work done is equal to the change in kinetic energy. Now, how does potential energy come in? Well, we have the right-hand side here. Let me write this. The kinetic energy at the end minus the kinetic energy at the beginning is equal to the work. So let's write it here one more time. So I have kb minus ka will equal to the integral from points A to B of f dx. Now we said if the force is conservative, meaning the force does not depend on the path. So if I go from A to B, regardless of whether I go from A and pass B and then come back to B, it just depends on the initial and final positions. If the force is conservative, if that's the case, then we can integrate this. Now the integral of this, the integral, let's say the integral of f dx is just some function, g of x, right? It would be some function, g of x. So let's integrate that. So we get kb minus ka will equal to, the integral of f is g of x, and then we have to evaluate this function between points a and b, and so this will give us kb minus ka and equals to the function evaluated at b, I will just call it gb minus ga. So here is the problem. If you try to write this, collect the a's together and the b's together, just to show you. You will get this. You'll get kb minus, let me move the gb here, minus gb is equal to ka, move the ka here, minus ga. So this looks bad. It doesn't look, aesthetically, it doesn't look very nice. Mathematically it's correct, but aesthetically it's not. For conservation, we like to have k plus something and then k plus something. So what we do is we define a new function. Let u of x equal to negative g of x. That means the integral of f dx will equal to negative u of x. So u of x is the integral of f dx with a minus sign. That means f of x, if you integrate a function and you take the derivative of that, you will get the function back. So f of x would be negative du dx. So with that minus sign, so g at point B will equal to negative u at point B. So you have negative negative u, so this will be k plus u. K b ub equals to here ka minus ga, but ga is negative ua, so minus minus ua, so that's plus ua. And this is the formula for the conservation of energy. And this u here, the potential energy, comes from an interaction. It comes from a force. If it's the earth, it will be the gravitational potential energy. If it's the spring, it will be the spring potential energy. And if it's the electric field, as you will see next semester, it will be the electric potential energy. And so on and so forth. If you have friction in there, then you have to break down this force into the sum of two forces. A force that's conservative plus a force that's non-conservative, and then you do it that way. The integral for the force that's not conservative, you cannot integrate it once and for all, because it depends on the path that you take. Every problem will be different. But the force that's conservative, you can do this integral once and for all, and you come up with this formula. All right? What do you take from this? First of all, if there are no non-conservative forces, meaning there is no friction or other things like friction, then you can use this. You say the energy, the total mechanical energy at the end will equal to the total mechanical energy at the beginning. And I should write it down. Mechanical energy. So we're not saying just energy, mechanical energy specifically. What is mechanical energy? We give it, it is the kinetic energy plus the potential energy. And in symbols, it would be K plus U. That's the mechanical energy. And the law of conservation of energy, or of mechanical energy, the law of conservation of energy says the energy is always conserved, regardless of what happens. If you include thermal energy in there, it's always conserved. Mechanical energy, more specifically, says if there are no non-conservative forces involved, then the kinetic energy plus the potential energy will be conserved also, will also be the same. So it's even stronger requirement or stronger statement than just the total energy, stronger in some fashion. Okay, so now, So you should remember that whenever you have potential energy, the force experienced by the particle in that potential will be the negative derivative of that. So with that said, let me go to to this problem here. Okay. So I need a piece of chalk. Yes. We have the potential energy of a particle is shown. So here it is. This is the potential energy in joules, and this is x in actually centimeters. I should say centimeters. And they say, what is the force or the x component of the force? It has to be the x component because we're moving along the x direction. When x equal to 5, 15, and 25 centimeters. Okay, well, let's write down the solution. Put your solution. I know that the force is minus du dx. In this case, we have just straight lines. So here, at this point here, the slope du dx is the slope. And what's the slope? It's the rise over the run. So it will be, it's actually a negative slope. So it would be 10 over 10. See, the scale here is just more, it's not the same scale. So it would be 10 over 10. It's actually negative 10 because you're dropping. So it's negative 10 over 10. And so that's equal to negative 1. Negative 1 what? Negative 1, it's actually joule per centimeter. Joule per centimeter. So we need it in joules per meter. So, for, where is x equal to 5 centimeters? X equal to 5 centimeters is here. So it belongs to this potential here, to this segment. So the force there will be, so when, for part A, when x equal to 5 centimeters, we get F will be negative, du dx will be negative 1 joule per centimeter. But I don't want joules per centimeter, we need joules per meter to get the force in newtons. So times 1 centimeter, no, actually 100 centimeters. 100 centimeters for every 1 meter. Centimeters cancel, minus minus is a plus, and so that in that case the force would be positive 100 newtons. 100 newtons. All right, 100 newtons. Sounds good. Now, how about at this point here? Well, here it's constant and it's equal to 0. So du dx here is simply equal to 0. And so when x is 15 centimeters, somewhere here, you get 0. The force is 0. And how about here? Well, at this point, du dx, which is the slope of this line, what is it? Well, it's the rise over the run. It rose by 10, right? And then the run is from here to here, so that's a 20. So 10 over 20 is 0.5. So it's 0.5, and it's positive. 0.5 joules per centimeter. And 0.5 joule per centimeter, you change it to joules per meter, which is in Newton, will give me, you multiply by 100 basically, so 500 joules per meter, which is 500 newtons. So when x is equal to somewhere here between 20 and 40, we're looking at 25, so here is 25, we get F would be negative du dx, and then there's equal to negative positive. So it's minus 500 newtons. All right. I will just double check my numbers. Okay, just one mistake. 0.5 times 100 is actually 50, not 500. So that's why I always double check. Looks good. And all right, let us go to the next example. So let's read it together. It says Julie starts, not stats, starts. Julie starts at the top of a frictionless 60-degree slope from rest. So Julie is here. It's frictionless. So at first it's like a straight incline, and then it curves. It becomes like a part of a circle. Okay. Julie starts at the top of a frictionless 60-degree slope from rest. At the bottom, the circular arc carries. So at the bottom, the circular arc carries, and then launches her off at 3 meters high ramp. So she would go like this, and then in here, she's launched this way. Okay. It says, how far horizontally is her touchdown point from the end of the ramp? So here is the end of the ramp. The end of the ramp is here. It's the end of the ramp. And what happens is she would go like that. She would fall. The question is, what is this? How far would she be from here? Interesting. So we need to know the direction of her motion, this angle here. We also need to know her speed there. If I know her speed here, direction of motion, I have her velocity, I have her height, and we can do this. So first of all, let's see what this angle is. There is a little bit of geometry first. Okay, let's take care of that first. So if this line continues, they're saying that 60. This is the radius, and we know that the radius intersects the circle here with 90 degrees. So let me just draw a line like this, and let me draw a line parallel here. So if this is 60, then this is 30, because this is 90. 60, 30. So this one is 60. That is 60 degrees. So this is 30. So this is 30. I think opposite interior angles or something. I forget what they're called for geometry. So this is 30 and this is 30. Let me draw a line straight down this way. So this is 90. So we said 60, 30, 30. And these two angles are both equal. So this is 30. If this is 90, then this is 60. And this angle they're telling me it's 90, so this is 30. So now I know that this is 30. Okay. Well, let's see. And so if this is 30, then this is 60. And this is 60, so this is 30. Because these two add up to 90 also. So that's 30 degrees. Okay. So that angle is 30 degrees. So if we figure the velocity here, she's going at 30 degrees above the horizontal. So we need to figure out what the velocity there, what the speed is over there. So we will say, let's call this point 1, and this point here is point 2. So we will have the kinetic energy at point 1 plus the potential energy at point 1 will equal to the kinetic energy at point 1 plus at point 2 plus the potential energy at point 2. In other words, the mechanical energy here equals to the mechanical energy there. Why? Because we have no non-conservative forces doing work. Friction is absent, You just have the gravitational force. Yes, you do have the normal force, but normal forces do not do any work because they always act perpendicular to the direction of motion. So that cosine of 90 is 0. So the work done by the normal force is 0. So because of the reason I just stated, let's write down the solution. We conclude that the mechanical energy at the beginning will equal to the mechanical energy at the end. By end, I mean the beginning of the ramp to this point on the ramp. And then we will worry about the other part later. The energy at the beginning consists of the kinetic energy at point 1 plus the potential energy at point 1, and then the kinetic energy at point 2 plus the potential energy at point 2. Kinetic energy is 1/2 mv squared, so 1/2 mv1 squared plus the potential energy is mg times the height. Let's call that y1. The height from here to here is y1, it's 25. And then plus the kinetic energy at point 2, so this is point 1 and this is point 2 here. We'll worry about the point 3 later. Oh, equal to 1/2 mv2 squared plus mgy2. We notice that the mass simply cancels, and since Julie starts from rest at this point, we know that V1 is 0, so this whole thing is actually 0. This is 0. So we get the following. Let's move the Y2 here, and I just have, on this side, I have 1/2 V2 squared, because the mass cancels. I have 1/2 V2 squared will equal to, if we move this to the other side, we get G, and we will factor the G, so you get Y1 minus Y2. Multiply both sides by 2, so let me do that right here. Multiply this by 2 so the 1/2 goes away. And then take the square root of both sides, so I take the square root of this. The square root of this one will just be V2, the magnitude of V2. And now we plug in the numbers. So you get 2 times 9.8, and you have the square root, times Y2 minus, Y1 minus Y2. Y1 is 25 and Y2 is 3 meters. 25 minus 3. And so let's do that. So you get V2 will be, get my calculator, would be 2 times 9.8 times 25 minus 3 is 22. Take the square root of that, and you get 20.77 approximately. Meters per second. Okay, so now we're at this point here. So let's zoom into that. Eventually we would like to know where it would land. So here's where we are. We're here. We're above the ground by 3 meters. And you're heading this way. With a V equal to 20.77. This angle here is 30 degrees. And our mass will land over here. I'll call this here, and name that to be the y-axis. So y initial is 3 meters, the height is 3 meters. X initial is 0, that's the 0 point. And then x final is 0. This is x initial here at this point. So, as you know, this is kinematics problem now, because the only force is gravity that's acting. And so we need to find the x component of the velocity and the y component of the velocity. The x component of the velocity would be the velocity times the cosine of the angle. So it would be 20.77 times the cosine of 30 degrees. So let's do that times the cosine of 30 degrees. And that's 17.98 meters per second. And then the y velocity will be the 20.77 times the sine of 30 degrees. That's 10.39 meters per second. And so I will continue with it, making sure the camera is still recording. All right, so to figure out where it will fall, I have to figure out how long it will take it to fall. So let's use the equation for the y. I know that y final is equal to y initial plus vy initial, the initial velocity in the y, I should say, yeah, here, vy initial, meaning at this point, and this is vx initial. But remember, vx does not change when the only velocity, when the only force acting is gravity. Gravity only acts in the y direction, not in the x direction. So the x velocity does not change. So vy initial times the time, and then minus 1/2 gt squared. So I get y final is 0 because it falls to the ground. Y initial is 3 plus v initial in the y direction is 10.39 t, and then minus half of 9.8 is 4.9, and then t squared, and we have to solve for t. And so use your calculator. I think I will not waste your time. You get t equals to, let me use my calculator. So I get 2.377 seconds. That's how long it will take it to fall, to hit the ground. So we know that x final is equal to x initial plus vx times the time. There is no acceleration in the x direction. So we get x initial is 0, vx is 17.98, that's vx, times the time, 2.377. So 17.98 times 2.377 equals to 42.74. So 42.7 approximately meters. So let me just double check if I have everything correct. Yes, according to the book, just approximated it to be 43, so 42.77. Probably the hardest part in this problem is the geometry, is the angles. So draw a nice picture if you're having trouble with this. Draw a nice picture and try to figure it out. All right? So I will stop this one, and then we will do 2 more problems in the next video.